Hi, I'm Yu. I'm going to talk about Clifford algebras and quaternions. First, we're going to define Clifford algebras CON as a R vector space with basis E1 to En, satisfying that ES ER equal to negative ER ES if S is not equal to R and R squared is -1. So and ER squared is -1. So for CON, we have the R basis that's corresponding to the increasing sequence. So for CON, we have CO1, we have 1 and E1 as the R basis, and CO2, we have 1, E1, E2, E1, E2 as R basis. So we can see that the dimension R of CON is 2 to the N. Next, we see that CO1 is isomorphic to the complex number, and CO2 is isomorphic to the quaternions. So for CO1, we have basis 1 and E1. So this is corresponding to the real part and imaginary part of a complex number. For CO2, we have basis 1, E1, E2 and E1, E2, those are corresponding to the 4 bases in a quaternion. We notice that there's a map Jn from Rn to Con defined on the basis of Rn and Con. That's basically just maps the basis of Rn to Con. So here the Rn is the basis of Rn, and it gives after Jn we have the basis in Con. So also we can see that this map Jn is injective. So we have the proposition that Jn on the element of Rn squared is a negative norm squared. So notice that this norm is still defined on Rn. Later on, we'll define the norm for Con. So here's the universal property of Clifford algebras. So if we have A as an R algebra and there's a map F from Rn to A, that's satisfying that fx squared is negative x norm squared, then there's a unique homomorphism F from Con to A that F conjugate with Jn is the little f. So here we can define a map alpha 0 from Rn to Con here. And we can verify that the alpha 0 squared is equal to the negative norm x squared. So this satisfies the requirement of the little f we want in the theorem defined before. So next, by the universal property of Clifford algebra, we have there's a unique alpha, for which alpha conjugate with Jn is just alpha 0. So we see that alpha on the basis of Con is just the negative of that basis. So we notice that if we have even number of bases of Con multiplied together, the alpha would just give us the identity. And if we have the odd number of bases timed together, we'll pick up a negative sign after alpha. So we can define the plus of CLN that is for the U after alpha, we still gets back U. And for also the negative CLN is that after alpha, we get the negative U. Here we can define the conjugation of Clifford algebras, that is by the reverse of the element and then picking up the negative sign. And we can also show that alpha on the conjugate of V is equal to alpha V conjugate by expanding all the bases. And we can also define the inner product of CLN on the basis of CLN. So if all the bases were aligned to each other, we have 1 or 0 otherwise. So finally, we can define the norm of X, norm of CLNs. It's just the X time dot product with itself and then take the square root of that. So next we move on to Clifford group. Clifford group gamma n is a subgroup that for U inside CLN not including the 0, and for the X inside R, we have alpha U X U inverses still inside Rn. And we notice that for the U in Rn and X in Rn, the alpha U X U inverse is still in Rn. So we can say that Rn is a subgroup of gamma n. We also have some really nice properties of gamma n. It is a closed subgroup of CLNX. And if we have U in gamma n, then U after alpha and U conjugate is also in gamma n. So we notice that there's a continuous group action that's CLNX on CLN to CLN defined by U and X is alpha U X U inverse using the definition from gamma n. Here UN is in CLN and then X is in Rn. And next, if we restrict the U inside the gamma n, this whole thing would be inside Rn. So we can define the map rho U, that is the rho U on X is just alpha U X U inverse. And we see that rho U is Rn to Rn for the U inside gamma n. Next, we see that the rho U from Rn to Rn is an isometry. This is proven by some properties about the norm that we talked about before. So we can see that rho U apply on X, the norm square of that is equal to the X norm square. So we see the rho U preserves the norm. So we can see that the result, like the row U, is like the map that preserves the norm. So we have row U inside ON. And then since U is in gamma n, we can think of row as gamma n to ON. Next, we are going to define the planar and spinor group. So for planar group, it's essentially like the first part of the definition we see are the same as gamma n, but it's just like has this extra condition that the U conjugate U is 1. So we can think of this condition as the U having the norm 1. So because before we define the norm of Clifford algebra as like the U dot U takes the square root, which is like the U and then square root of that. So this condition is just like enforcing the norm of U B1. And then for spinor group, we have the definition is just like it should be inside ping n, but it's also inside the plus CON. So yeah, we have the extra condition that U is inside CON plus. Next, we can show that the n-1 sphere is the subgroup of ping n. And then if we restrict the row U on U inside Sn, we'll get the reflections about hyperplane that's perpendicular to U. This is shown by if like x times U is 0, we have x, and then negative x if x is equal to TU for some t in R, which this is the definition of hyperplane reflection. And the details of those rules we won't prove here. So next, we have already seen that the map row restricted on the unit n-1 sphere is hyperplane reflections, and we also know that the orthogonal group is also generated by hyperplane reflections. So we can think of the row restricted to S-1 to ON is surjective. And also previously we have the theorem that the subgroup generated by S-1 is a subgroup of ping n, and also because the Sn-1 could generate ON onto the map of row, then the ping n on the map of row to ON is also surjective. So just a little digression from all the ping and spin into like the ON part. Previously in homework, we've shown that the row U from SU2 to SO3 is surjective. In homework 3, I think that's when we using the adjoint representations. So here we just like directly state the result here, and we'll see that we can prove this alternatively using spin. So we have seen that the row from pin n to On is surjective. And we have the property that the preimage of row, we have like if we restrict the row on spin n, then we'll have row from spin n to SON is surjective. We can see this because like pin n includes like both like CON plus and CON minus, and spin n would only have like the CON plus part. So this maps to SON, just like we can think of that having like the determinant 1 versus like the another parts of pin n like that's inside CON minus that's mapped to the ON part having the determinant -1. So here we can show that the S3 is isomorphic to S2 and it's isomorphic to spin 3. So we have already shown that S3 is isomorphic to SU2. So we only want to show S3 is isomorphic to spin 3. So spin 3 is inside CO3, and we see that CO3 has the basis 1, E1, E2, like so for those 8 bases. Because spin 3, we want it to be inside the plus part of CO3. We only want those bases having two products of those bases together. So we pick up the E2, E3, E3, E1, and E1, E2. Also, we need to enforce the norm is 1 condition. So we have to make the A squared plus B squared plus C squared plus D squared 1 condition. So this is suffice to show that, yeah, this is the same definition of S3. So this suffice to show S3 is isomorphic to SU2 and spin 3. So from this theorem, we can see, from the previous theorem, we know that spin n is, on the row spin n to SON is surjective, and also spin n is isomorphic to SU2. So SU2 to SO3 is also surjective. So this property here is like the main theorem that we have so far, and we will later on to see that how this would be applied to quaternions. So next we'll define quaternions in more details. So a quaternion Q is Q equal to S plus Xi, Y, J, Z, K for those S, X, Y, Z in R. And we also need to satisfy like the square and the multiplication rules. And we can also represent a quaternion as ordered pair for S's in R and A in R3. So we just want to check the quaternions is actually isomorphic to CO2 and satisfying all the requirements for CO2. So we can see that we think of like E1 to EJ, E2 to E1 to I, E2 to J, and E1, E2 to K. And obviously we have like the square of itself is just all -1s. That's great. And also we have this part that's ES, ER equal to -ER, ES. We can show it here it's corresponding to the like ij equal to k, jk equal to I rule. So we can define like some basic algebraic operations on quaternions. So the addition is defined element-wise on each basis, and then the product of two quaternions is a bit more complicated. There's like the dot product, and then also we of like the vector part, and also there's the cross product of the vector part. And SA, SB are just like some scalar added together to those like vector part. Yeah, we can show that the product rule we stated is actually valid by expanding all the bases and collecting terms. Then we want to define the conjugate of quaternion is just flip the sign of the vector part of the quaternion in the ordered pair notation. So we also define the norm of quaternion just as like the sum of the coefficient square and then taking the square root of that. And also we can define the inverse of quaternion. That is just we want the q times the q inverse equal to 1. And we have the form that q inverse is just the q conjugate divided by its norm. And then we define the unit quaternion as just like quaternion with norm 1. That's those coefficients square sum to 1. And we can see that for a unit quaternion, the q inverse is just equal to the conjugate of itself because the norm is 1. We can see that unit quaternion is isomorphic to S2. So we already know that S2 is isomorphic to S3. And by the definition of the unit quaternion, we need the 4 coefficients square sum to 1. This is corresponding to the definition of the 3-dimensional unit square, a unit sphere. And we define the pure quaternion as the quaternion only has the scalar term, and with the only has the vector part and the 0 scalar term. So we can show the special case of quaternion product. So here we have a unit quaternion Q equal to S and lambda V. V is like the unit vector part satisfying this rule. So we can verify that Q is indeed a unit quaternion. And also P of pure quaternion. Sorry, why is it not? Sorry, my Apple Pencil just died. So we have the pure quaternion P, and it's having the 0 scalar term and P. And we assume that the P is perpendicular to V. And we want to see that if we apply the unit quaternion Q on the pure quaternion P, and then by the product rule, in the end, we'll get the result which is also a pure quaternion with 0 scalar term. Oh, sorry, just to mention that the reason why we want to use a pure quaternion is that it has 3 bases, so we can like it only has the vector part and those three bases. So the vector part, we can just like directly use it on the three-dimensional space, and then it's just like, yeah, the vector part is just corresponding to the vector in 3 dimension. And then we can see the results if we apply Q to P, we'll get a pure quaternion. And then if we set the S to cosine theta and lambda to sine theta, we'll have the result as cosine theta P plus sine theta V cross product with P. So here is just a visualization. So here we have the V unit quaternion, the vector part of the unit quaternion, and P, the pure quaternion. And they are perpendicular to each other. And their cross product, V cross P, is perpendicular to both of them. And in the end, we see that the resulting vector has a component in P and V cross P. So we have the V cross P here, and also the P part here. And we can see that the sine and cosine theta term would just give us nicely results that the vector is inside that plane, and then also the relation to the theta. So we observe that if the V and P are perpendicular, then applying Q to P is just rotating P around V by angle theta. So next we see the general case. So if V and P are not perpendicular to each other, then simply multiplying P with Q would not give us the pure quaternion. So we have to time the P inverse again. So here we're just like using the product rule and then expanding terms out. And then in the end, we'll have the results. It's looking like this. So this is indeed a pure quaternion. And then by setting S to cosine theta over 2 and lambda to sine theta over 2, this would give us the results like this. And this is still kind of hard to visualize. And we'll just show another example here. So we have the pure quaternion 0P for the vector part is just like J plus K. And we want to see how it behave like rotate around y-axis by the 90 degrees. So we can describe this by using a quaternion P that's cosine pi over 4 and sine pi over 4 times V. Here, pi over 4 is because by definition, there is a half angle here. So if we want to rotate theta, we apply the quaternion with only half the angle. So here, by applying the algebraic rule, we'll see that we'll have the result we want. We'll see the visualization here. So V is the unit quaternion, and P here is the vector we had before. And similarly, in the result, we have the V cross P part here. which is perpendicular to both V and P. And we also have the P part. Where's here? So we can see that the resulting angle is somehow like rotated by theta, and getting the results here we want. So just to conclude, we've already seen that we have, if we apply a pure quaternion Q, apply a unit quaternion Q on pure quaternion P by PQ inverse, we can get the universal rotations in 3D. And this is because that under the map of rho, and we also notice that the PQP inverse form is exactly the same as the rho we defined before. So this is because we have the rho SU2 to SO3 is surjective. So we also have the pure quaternion is isomorphic to SU2. So under the map of rho, we can express all rotations, which is SO3.